and a few people are asking like medical data on medical data have to do. So I already this also I already confessed, like while doing CNN we are going to implement all that medical images only we are going to take, and then we'll implement the sessions, the things. And of course we few people are asking for recordings, so that also already I think I have shared the result. I have shared the reply also for the video recordings, sharing of video recordings. That also we will share after completing the sessions only. We will share the recordings. So these are the maximum, most important comments from yesterday's feedbacks, and the others are giving very positive comments. Most of the people are giving very positive comments, and I'm really thankful that you are able to understand something and you are gaining something. It's not like a wastage of a session. You are getting some knowledge in ML and DL. So yesterday we have started the basic concepts of DL. So today, for few minutes, on the first off before quiz, we will see few things, a deeper level of deep learning concepts. We will just dive into a few concepts of deep learning, and then after quiz, we will see how to implement the sessions in Google Colab. So whatever we are learning, the activation functions, the layers, whatever we have learned yesterday and today, that we will implement after quiz. I mean, second session, next session will be the complete implementation. So now we'll see a few concepts today. I just want you to introduce the basic concepts of neural networks, the activation function, loss function, and regularization. And these things will be the implementation part, what we are going to do after quiz. So first thing we will see. First thing is like activation function. So yesterday I already told you why we have to use an activation function for a neural networks. So just like our brain works like some neurons, that some element should be there in our hand or something. Whenever you get a signal from our brain, some element, some device should be there in our hand that will activate some neurons, either my right hand neurons or left hand neurons, to activate to give the information to that neurons that you activate at this particular time. So like that in machines also, while doing neural networks also, there should be something, some function or some logic or something should be there that should tell a particular neuron for a particular algorithm that in this time you have to activate more, or in this particular time you have to activate less. So that is the main function of a activation function. That will tell a particular neuron that when to on and when to off. That is the first function of an activation function. And the second main use of activation function is to introduce some non-linearity into that inputs or into that elements. So why we have to give some non-linearity? So I'll tell just asking have a robot, and you will ask your robot to make some sandwich. So you have trained your robot that you keep a bread and just slice something, just pour some butter on that, and then you keep another bread. It will make a sandwich. You have trained your robot like this. So without activation function, just you are giving some input, some hidden layer, and some output layer. That's it. I'll show you the diagram. So this is what. So here no activation function we have used. So here inputs are giving like a I1 and I2. These inputs are processed to some hidden layer where we have only 2 layers. And for the hidden layers, we are adding the weights, and of course some bias we are adding. So these things, this summation is going to this hidden layer, and then whatever functionalities, whatever activation function, I mean whatever mathematical analysis will do here, and we will come across to the output layer. This is the basic structure. So what will happen now when activation function is not there? then your robot always makes only one linear slices, like it will bread and then keep the butter, the bread, the butter, make, it won't change anything, just like we got in our linear. There is no creativity there, there won't be any much, no, it won't think about anything, just some linear, it won't do much effort. If the data is not clean data, if the data is completely a different, a complex data where the insights of data you can't able to understand, in that cases also it won't try to understand the data. Normally deep learning we use for complex data, but in that cases also it won't able to understand the data, just it will do whatever the function it has to do, take the input, add the weight and add the bias and make it to hidden layer. It won't think of new things. So uh, to do that, after some iterations, what happens, the logic whatever model you are building, that will become a completely waste model, because the complexity of data is increasing. Deep learning main concept is the features, it has to some creativity is losing, then that will be a complete linear model, just like our linear function. To reduce that, we will add some non-linearity to that machine. So non-linearity here means, instead of just building a bread butter, just we will tell that robot that you add some more. The robot can able to think that I can add some red chilies on that, I can add some lettuce on that, I can add some tomatoes on that. So that creativity you are adding to your mission. So that is nothing but an activation function, that is like adding some non-linearity. So while adding that non-linearity, there are different activation functions we'll use. So we can use any type of non-linearity to your particular application. So the different non-linearities are, so the first activation function is a linear function. So linear function is just like a normal straight line, y equal to x, a normal straight line. That only we are giving. So whenever we are going to do a simple problems, whenever we are going to use a regression analysis, that cases we use this linear function. Normally when a simple data is there and you want to use your neural network, you want to check your neural network there and you want to do some numerical analysis, there you'll use a linear function. So here for the linear function, the equation is y equal to x. It won't add any special creativity, only it will add a just normal linearity, a linear function. It will create in that weights and inputs. So next activation function we normally use is sigmoid function. So sigmoid function, for example, the example I am taking. So now it is making pictures. Sigmoid is like it will work between the curve will be always from 0 to 1. So if you see the linear function, it will be just like a straight line. So if x is increasing, that y will increase. Or when x is, sometimes the y will decrease. But in sigmoid function, if you observe the curve, so here the x value is between somewhat 2 to 2.5, 2 to this minus 2.5 to 2.5. In this particular small deviation, the y has a vast deviation here. So for this x will have a small deviation whenever you have a very small deviation in the x, but y has a very complete deviation. Means that the action, the algorithm will able to complete. Maybe it is into a simple range. It is in a broader way that every detail of data in a, well, we are just that linearity to the data. We are adding the activation function to the data. So this is what normally sigmoid functions we use for here. This is the equation for sigmoid function. Already this thing we have discussed. 1 by 1 plus e power minus x. That e power minus x is nothing but again y equal to mx plus c. That complete equation we are going to keep it here. And this is non-linear course. And notice that the x value lies between minus 2 and 2 and the y value is very steep. So for a small change also we are getting very high deviation. And this always steep between 0 to 1. It always lies between 0 to 1. And normally the sigmoid function is used for output layer. For the output layer, each and every layer we have to add some activation function. After taking the input values, we have to add one activation function. After operating in the hidden layers, again we have to add some activation function. Again, after getting the result from output layer, then again we have to add some activation function. So the sigmoid normally uh, at our output layer generally. So next one is ReLU. ReLU function is it states only the value is positive, then it will take the value. If otherwise, it will ignore that value. Just like your robot is making some sandwiches, so you applied some non-linearity there. So what it will think, if the ingredient is good, then it will consider that ingredient. If it taste is better, it will consider because it is a positive value. Otherwise, it will ignore that ingredient. That's how a ReLU. Sigmoid means it will take that it will take value, a range between whether it is it is the taste is a good or a little bit better. So that values, that range it will take, but it won't take after one. More outages, more better or more deviation, it won't take. It won't consider the sigmoid activation function. But ReLU only consists of only positive values. If it is not a positive value, just it will ignore that weight or that input, anything. That node it will ignore. And compared to all other activation functions, ReLU is the best activation function and very easy. So when you are doing some neural network program, so at particular layer you don't know what activation function you have to use, then happily you can use ReLU. So by there won't be any disadvantage at any point. Only it will take the positive values and it will reduce the ignores that remaining values. That's it. So at the hidden layers, that the best option is using ReLU. Okay, let's start now. Now the next activation function is tan H. Tan H is like it will take the end here from minus negative values to positive values. Just like our robot example, it will take a minus spicy values to a positive sweet values. So everything it will take, every all negative and positive values it will consider. But sigmoid it won't consider. It will consider only 0 to 1. And ReLU will consider only positive values. It will ignore all the remaining values, whether it may be a 0, whether it may be a negative value. So only positive values it will take. Now that tan H will consider all the values, just like minus spicy values to positive sweet values. Anything, any value it will take. So tan H mostly used at the for the hidden layers when you are using for multi-layer classification or when you are working with multi-variables in the output layer, when you have more variables you want to predict, in that cases particularly tan H is very useful. So this is the function we use when you do that activation function in the program. This is the function you calculate, you use for your syntax. So this is the function tan H. And next another important activation function is softmax. Softmax is completely about probability. So it won't give any integer value at the end. Normally for the output layer, we use either sigmoid or mostly softmax will use the activation function, because at the output layer, instead of deciding this is the value, some integer value is the output, instead of deciding that, we'll just take the probability. That will be a better one to take the decision depending on which neuron you have to consider as the output. So to decide that, instead of calculating an integer value, calculating probability is the better option. So softmax will give you everything as a probability. So this is the function how it will give the probability. So it won't give any real value. So it will always give the probability. So it is a non-linear and usually used when trying to handle a multiple classes. And softmax function was commonly used in the output layer of image classification problems. So when you are doing an image classification problem, the output always we are going to take either probability. We can't be completely we cannot justify that that is the perfect output point. So we cannot completely justify that. At some point of time, maybe we will come to a result in that maybe or may not be. In that cases, particularly we use a softmax activation function. That we'll see how we'll do that in our hands-on. So these are the activation functions what we use normally. So better once we'll recall all that activation functions. There are four: sigmoid, ReLU, tanh, and softmax. Linear function normally we won't use. Very rare case we'll use linear. It will not be treated as an activation function. Just a linear relationship it will create. So this is what about activation functions. So activation function main use is to activate a particular neuron and to create some non-linearity in the data set. That is what activation function is. The next concept is loss functions. So loss functions already we have discussed in even while discussing about the machine learning as a linear regression. So loss function is nothing but the difference between the error, whatever comes between actual value and predicted value. So whatever difference between the actual value and predicted value is nothing but the loss function or cost function. So here any machine learning algorithm or any deep learning algorithm aim is to reduce that loss functions. For that we are using stochastic gradient. We will derive that loss function and will equate to zero, and we will use we will use that back propagation. Everything will use to reduce the loss functions. So but how to calculate that loss function? Some error will come. Suppose we are using activation function as probability, I mean softmax. So at the end of that output layer, you'll get the probability. Now, how do you calculate the loss function? How do you calculate that particular? This is the error I have received from from actual and predicted. If it is a single integer number, directly I can differentiate the both the things. I can number, but in real case that won't be like that. In real case there will be a high dimensionality while using a deep learning thing. So suppose if it is a images, medical images, so in the output there will be a high dimensionality medical image there. So there, while from actual to if you want to take the actual to predicted one, you can't tell this is the real number of error. You can't tell that. There should be some function to predict all these things. So that function is called a loss function. Loss functions in deep learning are essential for measuring how well or poorly your model is performing during training. This guides the optimization process by telling the model what kind of error it is making and how to adjust its parameters. So there are different ways we can calculate the loss functions. So first one is MSE, mean squared error. So mean squared error is, so this thing better I'll explain with an example. Just think you are a chef and you are making some dish, and you have a different type of customers you have to check your quality of food whatever you are making. So there MSc is like suppose MSc is normally how it will take means it will consider only the large errors. If it is a minute error, it will neglect. It will consider only large errors. Suppose uh, if your dish there is some 0.01% of salting, so it will frown. The judge is if the judge is like MSc, he will frown. That's it. He won't do anything. But 90% of sweetness is there. It shouldn't be there actually. Maybe you cannot make it very sweet, but you have made 90% of sweetness in that dish. Then automatically he'll throw that plate. So like that MSc works. So MSc always concentrate on the large errors. Wherever suppose I have 100 nodes in the output layer, in that 100 nodes, some 70 nodes are giving very large error and 30 nodes are giving very less error. So that 30 nodes will be ignored, 70 nodes will be considered, and that errors will be squared and summarized and given back to that hidden layer, activation functions and optimizers. This is how MSc will work. So MSc means mean squared error. So normally MSc we use for regression problems, and this is the equation we using this equation will calculate loss function in regression problems. So we will take the error between the actual and predicted and we'll square it and we'll summarize that. We will add all that errors and then we will give that complete average error to our optimizer. This is how MSc will work. Next, MAE. MAE means absolute error. There won't be any square. It's just absolute error. This is like if we are judges like MAE, so whatever mistake you do, he won't frown at yourself. He won't, he won't be so much angry towards you. So whatever may be the error, whether it is a big error, whether it is a small error, he won't be so much angry to you. He'll just completely say, yeah, you did very well, but you have to improve in this particular manner. So he'll tell that particular area where you are lagging. So that what MAE will do. So MAE will not concentrate, MAE will not differentiate between very small error and very large error. It will tell you where that particular node is, giving some error. In that particular node, you can able to analyze something or you can able to analyze something. That what MAE will do. So it will take the difference between the actual and predicted and then it will summarize and it will give and back to optimizers. So this is also normally we use for regression problems. So next thing is cross entropy loss. This cross entropy loss normally we use in classification algorithms. So for the classification algorithms, binary classification, particularly binary classification and multi-class classifications, this cross entropy is like depending on the probabilities. Like for example, the same example I'll take. So now your judges, you have made some dish and now your judge is a cross entropy loss. So you have in the initially you declared that you are going to make a chocolate cake, but something you have made the dish and finally the result is like a vanilla cake. So automatically your dish is not accepted. So that is completely lost. Cross entropy will not accept that. But if you have made chocolate cake, but only some 20% of chocolate is there, the remaining is something, then cross entropy will accept that and it will analyze that and it will given back that function to hidden layer or optimizer to improve better. But once you said something and you have given completely different to that product, it will not act. It will stop the process there. It will give you the complete 0% accuracy. So this is what happens in cross entropy. So normally this thing we'll use for classification algorithms. Anyway, classification algorithm I told you At the end of the prediction, we will get all the discrete outputs. There won't be any dependency between the outputs. So just you have to categorize anything. In that cases, particularly we use cross entropy values. There won't be any probability. There won't be any integer values. Just it will tell. It will see that whether whatever your actual value is there, how much near your predicted value, how much near. At least it should be some 20% or 30%. Then only it will accept. So this is the equation we use for our cross entropy. This is for binary classification and this is for our multi classification. So these two formulas we are going to use for our loss functions. And the next one is hinge loss. Hinge loss is nothing but support vector machines. In support vector machines already we have discussed, instead of a line, separation line, we will use a plane to separate the data points, data samples. So in that particular case, we will use the hinge loss. This hinge loss is used for maximum margin classification. So we will give at the starting itself. You will tell that judge that I am going to make a chocolate cake. This is my maximum probability of getting the accuracy. I mean, in the starting itself, we will tell that range maximum 20% chance I is there to whatever I am going to make, that will be a chocolate cake. So maximum 70% chance. So you have to reach up to 70%. That is enough. If you are reaching up also, it's okay. But you cannot reach the bottom level of 70%. There, then if your chocolate cake is not up to that 70%, then hinge loss will come and it will give you the function. It will work function and it will given back to the hidden layer. So this is hinge loss. So this is the formula what will take at hinge loss. And Huber loss is like combination of MSE and MAE. Both will combine together. The squared error and absolute error will combine together and will pass back. Will pass it to back propagation. So these are the losses we use for our end of the output layer to calculate how much near we are coming to our actual value, how much machine can able to predict the value very close to our actual value. So this is how we'll do that. And the next concept is, I hope you understand the activation functions and loss functions. And next concept is regularization. So regularization is nothing but it will train the data set in a it will see that the model is whatever algorithm, whatever machine learning model or deep learning model we have made. It will regularization techniques will keep that model only focused on the data, only focused on the training, only focused on the accuracy. So it will reduce the overfitting problem. Just think you are a basketball coach. So you want your final aim is you want to make your team should focus on the winning the cup. That's your focus. So in that cases, it cannot be turned to some other areas. Some other factors should not influence your data set. Your data set is there is your team, basketball team. Just think that. So that is what regularization will do. So regularization always look at the data and look at the training, look at the model. So wherever some overfitting happens, it will reduce that and it will make the model better on the training, testing accurate. So this is what regularization will do. In regularization, we have different concepts again. So first concept is like our L1 regularization, that we call it as lasso regularization. So lasso regularization is nothing but this is the formula we use for lasso regularization. It will add some penalty. So yesterday I told you some amount is increasing, the data overfitting loss is increasing. To that, we will add some penalty. So the penalty is nothing but the element which is completely irreversible to this loss function. So, for example, the same basketball team we same basketball team we are considering the same basketball. So lasso regression is like, suppose a few people in your team are just for showing off. They are not playing. They are not. They are not participating in the team activities better. So you are the team coach, and regularization is the team coach, and it will tell like, if you are not participating, you'll be benched. You'll sit on the bench. And if still that sir participate, then remove that permanently and just make it like a dead end, dead note. That is what lasso regularization will do. So whatever nodes are not participating actively in the data modeling or pre-processing or whatever training, that nodes will be removed completely and keep it as it. Just like we'll make it as it. That's what happens in a lasso regularization. The next type of regularization is ridge regression. So ridge regularization is, we call it as L2 regularization. So in L2 regularization, some few people are not participating, but instead of deleting them permanently, it will tell that it will compress their strategies. It's like basketball means basketball team. Okay, have a 5 minutes break. There is so many comments in audio quality. So we'll have it. Now we will share the quiz link. You please do that quiz link. Now we'll check the audio quality and I'll come back in 10 minutes. So I'm getting so many comments on the audio quality. You can't able to hear. So we are sharing the quiz link now. We'll move on to the session. And now before to that session, most of the people are not able to hear the voice. So again, I'm repeating, we have discussed the activation functions and of course loss functions. Now we will see the regularization functions. What so regularization actually it is to reduce the overfitting problem. It is to eliminate the overfitting problem. To make the model concentrate complete focus on the training data. So it is to eliminate the overfitting problem, regularization. We have different types of problem. We have different types of regularization techniques. Still, am I not audible? So regularization techniques. Regularization techniques are used to overcome the overfitting problem. Now let's check whether am I audible now or not. So now is it clear? Is it clear, everyone? Am I audible? So let's continue the regularization part. So the first type of regularization is L1 regularization. That is, we normally call it as lasso regularization. For example, I already told you the example. Just assume that you are a basketball coach. The regularization is a basketball coach, and your main aim is to focus your complete team to achieve a goal, to achieve a medal or achieve a cup. So that is your final goal. So that is, just assume that your basketball team is like your data set, your model, deep learning model, what you are building. So L1 regularization is, lasso regularization is just like, suppose in your team members, some nodes are not actively participated, just they'll show off something, but they are not participating completely in your teamwork. In that particular thing, your regularization as a coach, it will tell to that particular nodes that if you are not completely participating in the training or whatever team activities, you will be eliminated, you will be benched. That's what L1 regularization will do. So if still that nodes are not participating well, then that will be removed permanently and it will keep aside. It will just treat it as a dead notes. That will not be workful any further process of our data modeling or any other algorithms. We will not use that nodes. So that's what L1 regularization will do. So here we will add a penalty equal to the absolute value of the magnitude of coefficient. The penalty is nothing but whichever completely reverse to the loss function. So why I am adding that penalty to that loss function means, if that penalty, if I increase, we will add both the magnitudes of these two are completely reverse. It's both are reversely proportional, inversely proportional. So whenever this is increasing, the loss automatically will reduce. So when this is reducing, the loss automatically will increase. So this thing will be in our hands to reduce the penalty or to increase the penalty. So whenever you increase a little bit, the loss we can able to reduce that. So this is what regularization work will do. So this is what L1 regularization. So the particular nodes, it will be removed completely. And second type of regularization is L2 regularization, that is ridge regression. So ridge regression is like, instead of adding the absolute value as a penalty, it will add the square value. Square value it will add as a penalty. So here that lambda is the activation, regularization strength, the value of the how much value you are adding, how much penalty value you are adding, that is decided by this lambda. This is the regularization constant, we call it as. This is the lambda. So here in ridge regression, for example, if you are taking the same basketball team, L1 is completely remove the nodes, but L2 will not remove completely, but it will reduce the strategies of that particular nodes. So it will reduce the importance of that particular nodes, so that for the next being algorithm or next process, that nodes will able to actively participate from the feedback that if I am not participating, I will be eliminated. That that nodes will know that, and then next process it will be actively participated. So what I mean is, L1 regularization, the nodes will be completely removed, but in L2 regularization, it will not be completely removed. The nodes will be there. It won't be like a dead nodes. It will be there, but the participation or the strength of that particular node will be reduced, compressed. So the participation will be reduced a little bit. The other nodes activation participation will be increased more, so that particular nodes will participate more and these nodes will participate less. So by doing that, by changing or updating the weights, we can do that. So automatically the loss will be reduced, the overfitting problem will be reduced. So the third type of regularization is dropout. So dropout is nothing but, if just like the same example I am telling in a basketball team. So few people are very strong, some nodes are very strong and some nodes are a little bit weak. So what we'll do as a coach, if regularization is a coach, as a coach, what you do, you maybe in the starting match or some unimportant match, we will make that strongest participants to sit on the bench and the other participants will improve their skills more, just like our normal cricket matches. So at the final match, all the strong participants will come over and play, but at the starting level they'll give some rest, and the remaining some next secondary participants, secondary players will come, and they play in the starting level or something. So the same thing happened in dropout regularization. So dropout regularization, the strongest nodes which are actively participating and which are influencing more, which are giving more information, that nodes will be uh, stopped for a particular time, and the other nodes are made to participate more. So at the final layer, so all the participants will have the equal capacity, equal strength to participate in the building algorithm, in modeling algorithm, or in training algorithm while training. So whatever may be the process in that modeling, but at the final stage, all the nodes should have the equal participation. That is the main aim of dropout algorithm, dropout regularization. By doing this, it will see there won't be any overfit of data, overfit of data or any more other noises. So every node will have the same consistency at a particular after a particular time. So that is the main aim of dropout. Next thing is early stopping. One more type of regularization is early stopping. So early stopping is nothing but same example I am taking, the team. So when a player is continuously playing, when a player is so many iterations he is doing, and after some point of time, the coach will know that if he is stressed more, next iteration he cannot able to performance at the final. When the final match comes, he cannot able to performance. So what he'll do, at a particular level, he'll stop that algorithm, he'll stop that practicing, and he'll make the player to go and rest. That's what we do in early stopping also. While training the algorithm with particular nodes, if we train so much with the data, uh, that there will be, like in our starting days we have discussed overfitting and underfitting. So if we train too much of the data, then the algorithm will learn more, and it will create some complex curve. So to reduce that, at a particular point we'll stop training, will stop the algorithm to train itself. So that point is called early stopping. So maybe after that point, instead of training, there won't be any much change. So there will be something like, after some point of time it is vexed, and it won't train itself, it won't learn any new things. It's just something like a normal curve, a linear curve. At that point of time, it is wasting to the mission, or it is wasting, we are wasting the energy, we are wasting the storage. So to reduce that problem, at a particular point, wherever that curve is making linear, at that particular point we'll stop early, the training period will be stopped early. So this is one type of regularization technique to reduce the or fitting problem. And the next one is batch normalization. So batch normalization is nothing but whatever nodes or whatever data points are there in your data set, or whatever information you have in our layers. So you just make sure that all the points will have the same consistency at the same level. Mm, Suppose I have a table, Excel table, and I have some points like some 10, 100, or something, some column I have some 10,000, 20,000, or 30,000. So what I'll do, I'll use some functions just like mean, or some maximum number I'll take from that column, or some mean I'll take, or everything, every number I'll divide with something, or I'll take a constant number and I'll take all the differences of that column or rows from that constant number. So whatever may be the statistical method I use, I'll just keep complete Excel data should be consistent. Everything should be a normalized one. Everything should be in, just to for a viewing purpose, everything should be in a same range. That is what called normalization. So by doing that, you will reduce the randomness of your input data, and you can reduce the noise of your data, and everything will be consistent. So it is easy to it is easy for the machine to understand better the data. So this is a type of regularization technique. The next one is data augmentation. This is one more type of regularization technique. So data augmentation is nothing but, for example, the same basketball team I'm taking. So when the player is playing something, when he's playing seriously, when he's playing, just to give some noise to him intentionally from the external source, you give some noise, like play some loud music, or you just some other, you ask your subordinate sub coach to scold them very loudly, you shout very loudly, so create some noise just to check whether the player is deviating from his work, or he is able to concentrate, he is able to focus more on his game. That is data augmentation. So in data augmentation, we will create some noise. We will instead of giving the same data set, we will just do some operations on the data set. We will rotate that data set. We will scale that data set. We will add some more resolutions to that data set. Some operations will do, and we'll create some disturbance in that data set, and will produce that to machine learning model. Then also that machine learning model has to it has to capable of understanding the data, and has to create the model effectively. That is what data augmentation. So data augmentation mostly we use for our image processing. So in the image processing, while doing deep learning fusion techniques, in fusion techniques, we will apply all the data augmentation process. Suppose for my data, I have image data set, I have only 10 images I have, but for a neural network, I need some 10,000 images. So what I'll do, for taking that 10 images, normal first image I'll take, I'll apply all the data augmentation techniques. So I'll rotate that picture, I'll resolute that picture, I'll scale that picture, I'll minimize that picture. Some operations I'll do, I'll make that one picture into 10 pictures, so that the 10 pictures will make that into some 100 pictures. Again, I'll do operations on that 100 pictures, and I'll make finally some data, 10,000 data sets. The meaning is not changed, just I included some noise and some disturbance, and I created more and more data sets in using a data augmentation. So that is what data augmentation. And next thing is weight sharing. So weight sharing is nothing but, suppose the same basketball team I'm going to take. So normally for a player, he'll have a unique number as a jersey to identify that particular person. He'll have a unique jersey, some unique dress, unique number he'll have. But just assume each and every player will have the same number of jersey. So what do you think? If you are a regularization is a coach, so regularization will tell you that, okay, whatever may be your number, you have to play with the whatever may be your position. In whatever position you are, just play with the same number. Means the same thing happens in our data set also. So wherever that node is there, wherever the strong node, wherever the simple node, wherever that position is there, but it has to perform the same thing whatever the input layer is performing. Suppose that the same node is there. For example, I'll tell you one more example. I'm taking an image of dog, and I am going to process the image of dog to some my nodes, and I have predicted the output as dog. That is over. One project is over for me. So in the next project, the same dog image I am going to take, but I am going to add uh, a cat in that picture. So I have the same dog in my picture and the picture also, and also I have a cat picture also there. So instead of again creating the same features of dog, I'll share the weights of whatever features, whatever nodes I have created in my previous experiment, that I'll take here, and I'll share the weights here, and I'll the remaining weights only, the remaining nodes only I'll create. So weights will be shared from one layer to another layer. And instead of creating all that, the weights will be shared to all the layers. So the same weight will be worked in the input layer, the same weighted node will be worked in the hidden layer, The same weighted node will be worked in the output layer. So the node weightage will be same. Everywhere the node weightage will be same, but the position is different. That is what the weight sharing that normally we'll use in image processing. CNN mostly we use this weight sharing everywhere. Whenever you are going for a bigger images, you are going to use your weight sharing. And the next thing is noise injection. So noise injection is nothing but just adding some random noise, just like augmentation, just adding some random noise to that data set. So by adding noise, just like our GenAI, the basic concept is adding a discriminator and a generator. So one thing will predict you positive things, and one thing will predict you the reverse things. They'll compete with each other and give you the best result. So that's what happened in a noise injection. Also, we intentionally add some extra noise to that model. So by using that noise also, the machine learning model, whatever deep learning model we are creating, that has to come out and it has to give the best results. This is one type of technique we use to reduce the overfitting. Next one is elastic net regularization. So elastic net regularization is a combination of lasso and ridge regression. I mean regularizations, L1 and L2 regularizations. So we use the summation of the absolute values and also the squared values of the penalties, and we'll combine both. That will give as a function to the as a regularization function to the hidden layer. And next one is label smoothing. So label smoothing is assigning in just like when you are doing some mistake in a match or in your team. It's just like our regularization coach is now. So smooth labeling means it will come to you and it will tell, okay, you did better, but you have to improve more. There you are lagging. The same thing happens here also. When you are using smooth labeling, when the error is very big, when the node is not performing well, or it is learning so much because of the overfit. So at that particular time, smooth labeling will do. It will not eliminate that completely that node, but it will try to particularly work on that particular node. It will reduce the working of inform to the activation function that that node should be participated very less in that modeling, in the data processing, or whatever processing we are doing in a complete process. In that particular case, it will inform that activation function that this particular node you have to deal very lessly. You have to contact very lessly. Very no, not if not regularly. You need not to contact that node. So smoothly it will tell. It will not eliminate completely. Just but the working of that node, the participation of that node will be reduced. That is what smooth labeling. And these are the main concepts of deep learning when you are doing the syntax. And the next thing is the main elements of neural networks. This already yesterday we have seen, but just a reminder of again. So we have basically three nodes, three layers. So input layers, hidden layers, and output layer. Input layer, we don't do any mathematical operation on that. Any operation or any techniques, nothing will be used on the input layer. Input layer is just to store all your information and all that input information, and it has to pass that information to next layers. That's what input layer will do. But there won't be any functions we won't use, any operations we won't do on that input layer. The hidden layer is the main controlling unit where everything happens in our deep learning model. So there can be any number of hidden layers. If the complexity of the project is very more, then the number of hidden layers we can increase. So the hidden layers will consist of all that functionalities, all the mathematical relationships, all that algorithms, whatever we are going to do, everything happens in the hidden layers. And the last one is output layers. Output layers will be, it will aggregate all the whatever values it is coming from the hidden layer, and it will aggregate everything, all the values, or it will average that values, and it will give the output. If it is a back propagation, the output again will be sent to that hidden layer, and the weights will be updated according to the output. So these are the main basic building blocks of this output layer. And one simple concept I have left yesterday's class. So that is hyperparameter and model parameter. So this hyperparameter and model parameter is nothing but a model parameter is whatever happens when the model is trained. When a model is, when the algorithm is going on, whatever it is updating, that parameters are called model parameters. Hyperparameter is whatever values we are giving from outside. So just like KNN algorithm, the K value randomly first we will select. So K is a hyperparameter there. So learning rate, that we will give how much value it has to learn. So that is a hyperparameter. But here in the neural networks, the weights will be updated according to that, but that is a model parameter that will be trained. In that, depending on the trained or depending on the accuracy, the parameter will be updated by the algorithm itself. So that is a model parameter. This is the main difference between model parameter and hyperparameter. I hope you understand this. Now we'll see the Google Colab, how to do a simple deep learning model. So for the deep learning, actually for machine learning, up to now we have used normal libraries like NumPy, Pandas, and Matplotlib or Seaborn. Are these type of libraries we have used. For deep learning, we have to build a neural networks. For that, normally we go for TensorFlow, PyTorch, Keras library. Actually, Keras is a library. We normally use TensorFlow or PyChart. Scikit library is not most usable for deep learning thing. It will be used for normally machine learning algorithms. So when you are going for deep learning, here I am going to use all the TensorFlow because it is very flexible and very useful to do all that neural network problems. And if you are using a Jupyter notebook, you have to again install that TensorFlow in your Jupyter notebook. So the syntax is pip install the whatever module you want. TensorFlow means you have to type TensorFlow. If you want to install PyTorch, then pip install PyTorch. You have to install in your Jupyter or Spider notebooks. But you are using a Google Colab, it's already defaultly all the modules are installed here. So just you can directly type import TensorFlow as TF. So shortcut name here I have imported as TF. So directly I can import this. Keyboard. Directly you can import that libraries from here if you are using a Google Colab. So the first step is here also in deep learning also consists of all the regular 5 steps whatever we did in our machine learning algorithms. First one is importing the libraries, second one is loading the data, third one is the third one will the building the model only it differs. So at the in machine learning we have built the model using the machine learning algorithms, but here we will create all the neural networks. So that only in that part it will differ, that we will see here. This project is actually I have some house prices, some area Boston house prices. I have downloaded the dataset from Kaggle. So house prices are there depending on some features, some area or some location or some square feet, nearby houses, what are the functionalities, what are the specialities you have. Depending on that you have to decide the house price. So this is the data set we have. So here first step I have imported the libraries, normal libraries, NumPy for numerical calculations and Pandas for data frames, and TensorFlow for here I am doing this project using neural networks, so I'm installing the TensorFlow. So first thing, I have imported the libraries. This already you know, that's why I'm going fast. Second one is, second step is loading the data. So loading the data here in my, this is the Keras library from the TensorFlow. In Keras library, normally when you are using TensorFlow, most of the neural network modules are related to neural network libraries. Everything will be, we can do using Keras. So first I have imported the Keras library. This is TensorFlow dot Keras library. In that, some data sets I have already default data set, inbuilt data sets. In that inbuilt data sets, I have considered that Boston underscore housing. So Boston underscore housing I have downloaded in a variable of H, and here I have splitted the data set like input, in the input in the training data set, this is my X, and in my training data set, this is my Y. Means this is the feature and this is the label in my training data set. In my testing data set, this is the feature and this is the label. So one feature and one variable I am considering for this simple project. This is a very simple, very basic project in neural networks. So for that I have considered only one feature and one label. Now for this H, for this variable I am considering and I am loading the data. So I have loaded my data. It is compiled successfully. And the next thing is, I want to see the shape of that my features, my features, my trained features. So the shape is like here already yesterday we have discussed 1D tensor, 2D tensor. So here I have this meaning is 404 samples I have, 404 examples like rows, 404 examples I have, and the dimensionality is 13. Dimensionality is 13. So layers I have formed like 13. 13 features I have, and one label I have, that is house price. I have to predict that house price. And the next thing is the building the model. So here the machine learning and deep learning will differ. So in machine learning, if you remember, we have downloaded the sklearn library. From sklearn library, we have imported whatever algorithm we are going to use. That algorithm we have downloaded, and then we fitted our X train and Y train to that particular algorithm. Suppose it is a linear regression, we have imported the linear regression, and we have given linear regression dot fit dot particular X train and Y train. But here it is some layers we have to form. So to form the layers, there are three methods we can use. One is sequential method, or one is a basic method, one is an API method. So sequential method is just like layers. We are going to keep the layers one by one. Sequentially, you are attaching one layer to another layer. API means somewhere you create all the layers and you create some API, and you take that API and you can upload the particular API here. Basic means there won't be any layers. You have to build from raw. From raw data you have to consider, and you have to everything you have to build it. So in that three, sequential is I feel that is more effective compared to all these things. So I have considered the sequential. So sequential, if I give sequential means all the layers will be connected. I have to represent whatever, how many layers I am going to use, that each and every layer I have to represent with the input and output. That is what sequential means. So I am keeping everything in my model in a variable like model. TensorFlow.keras is library, and sequential I am using. So in that particular sequential, here I am using three layers. So three layers I am connecting one by one. First one is my input layer, second one is my hidden layer, and third one is my output layer. So for my input layer, dense is nothing but each layer is connected to another layer. When the layer is connected to another layer completely, so suppose in my first layer I have two neurons, and my hidden layer I have three neurons. So this two neurons completely connected to that three neurons. Then we can call it as that is fully connected network or dense network. So if you are using a neural network, normally dense networks will be, if it is a dense network, then the accuracy will be more. So dense means completely it should be connected to each and every neuron of all layers. So here I am representing this. I am going to connect as a dense layer. So dense, this is my dimensionality 13. So there, while seeing that shape, you have seen already the dimensionality is 13, means 13 features, 13 axes I have in my tensor, and that in that number of axes I am going to use as my input nodes. So I am using 13 nodes in my first input layer, and my activation function for my input layer I am using sigmoid. Here this thing is your wish. Normally for the hidden layers I have told you, normally in general for the hidden layers the activation function is ReLU, and for the output layer the activation function is softmax in general. You can change that also depending on your application. So here it's just a linear regression problem. So I have used sigmoid here, and for the hidden layer, I am going to use only six nodes I can use. This while doing CNN, I'll explain you how to select nodes in hidden layer. So here it is a simple project, just a linear number I have to calculate. So I have used six nodes in my hidden layer, and activation function I am going to use is ReLU. And again, this is my output layer. So output layer, only one variable I am going to predict, that is house prices. So I have created only one node, and activation function here I have to use softmax. So instead of softmax, you can use here, as this is a linear regression problem, just a linear regression. House, some features are there, depending on that some some house prices you have to predict. So just a normal linear regression problem. So instead of softmax, here you can use that linear function, whatever we have studied, the activation function, first activation function, linear function you can use here. Softmax is when it is an images, you want to calculate the probability, then you go for a softmax. But here there is no need of probability, it's just a real number. So you can use linear also there. Just give linear there. I'll run it. So now my neural network layers are built. Then we'll move to next thing. Once it is fitted, now I'll compile. My layer is built. Now I'll compile that. Now I'll compile that neural network model. So my algorithm is built. So while compiling in neural networks, you have to concentrate. If it is a machine learning problem, so there while compiling you have to concentrate on the metrics, like only accuracy. You just fit that line and then compile, and you'll see the metrics like accuracy, recall, precision, R2 score, R confusion matrix. Only these metrics you have concentrated. But in neural networks, the main aim is to reduce the loss function. So everything will be propagated back, and you have to get the feedback each and every iteration. So for that you have to concentrate. Whenever you compile something, you have to concentrate what optimizer you are going to use, and what is the loss function you are going to use, and what are the metrics you are going to calculate. These three things are compulsory while doing the deep learning problems. So first optimizer is Adam. Optimizer is nothing but uh, to once the loss function is giving that value back to the hidden layer. So at the hidden layer, the optimizer will tell you what you have to do now. If the loss function is more, whether which activation function, it will tell the activation function that, see, this is the loss function, this is the loss we got from the previous one. So you do which nodes are better performed. So it will optimize that thing. It will tell to that activizer that you have to perform now. So otherwise you do some work, you do some work, it will tell that what to do now. it will analyze that error and it will it will tell what to perform next. That is the work of optimizer. So normal default, normally we'll consider the Adam as the optimizer, and loss function here I have taken as MSE, mean squared error, and metrics here I have calculated like MAE, because in regularization I already told you, I mean regression I already told you. For the regression problem, instead of calculating accuracy, normally we'll calculate R2 score. So R2 score, to calculate R2 score, we have to use either MSC or MAE or some mean mode, all these things. So here this is a normal regression problem. So here instead of metrics, I am giving accuracy. Instead of accuracy, I am giving MAE. So this is what compile. So these things are common to any deep learning problem. Now it is compiled, and then now I after giving what compiler I am going to use, what loss function I am going to use, what metrics I am going to use, and how my neural network layer should be there. So after giving everything, now I am going to fit my model, my data to this particular elements. So whatever elements we have created, I am going to fit my input and output training data set to that particular elements. Here epochs means each node and each node should pass from the input layer, from the hidden layer, from the output layer, and he has to give an output. So that complete process from starting to ending, that we call it as an iteration. It has to pass to at the end and it has to come back. So one iteration, that cycle is called one iteration. Like how many times I am going to train my data set. So here I am giving 10 epochs, means 10 iteration I want, 10 times I want all my nodes, whatever nodes I am using in input layer, 13 nodes. The 13 nodes at 10 times everything should be complete the cycle. So this is what I mean of epochs. So here see, if when it completed first epoch, mean first training, so we got that loss as 562 and some accuracy MAE is 21. For the second time, the same data set is passed. So second iteration, the loss is reduced a little bit. This MAE also almost same. And for the third iteration, the loss is still reduced a bit. So when it completed 10 times, the loss is almost very, completely decreased up to 518. The starting training, it has 562. Now the loss is 518. There is a big difference between the loss. And MAE also, it is reduced a little bit, not that much difference. So this is what, epoch means. Now we will evaluate our test data. Whatever test data we have kept is unseen. So that test data we have given. So these are the results. Already from the here that no actual data we know. So these are the result of test data. So this 4 by 4 means 4 times, 4 samples it is considered from the test data. Test data maybe some 30% or 20% we kept aside. In that 4 samples it is considered and 4 iterations it has done as for testing. 4 iteration, 4 epochs it has done. In that 4 epochs, the average value of loss is 542 and average value of MAE is 21. So this is the final average value. I mean, for the fourth one, this is the final average value, whatever we are getting of loss and MAE. So this is the simple project of deep learning, how to build a neurons. We'll see one more program. Anyway, this link we already shared to you. This Google Colab link we have shared. We're going to share now. And one more link also we are going to share it now. Poster house pricing we are going to share now, and we'll just see one more algorithm just like this, a simple algorithm. So artificial neural networks. Second one is artificial neural networks. That link also we are going to share now. So this is one more algorithm. So here you can see here I have imported the NumPy. So here I have imported the NumPy. So instead of taking some data set, I have created a simple features. Some here three, just like a matrix, I have created my features, and some labels I have created. Just assume this is some student is, that this is the reading time and this is the sleeping time. So first student, he has some 2 hours of reading time and 9 hours of sleeping time. So maybe this label we can consider as he passed the exam or not. That is my label. So he has 92% of, let's say this is failing the exam. So 92% of failing the exam. So that is the label I have considered, and these are features, some features. So for example, this is the reading time of student and this is the sleeping time of student. So here I have considered two features. So three columns I have, and these are the labels. Just randomly I have taken some number. Now so I already told you one step is normalization. When you get a data set, first thing is you have to make all that data points you have in a data set should be consistent. So for that you have to apply normalization techniques. So this is called normalization techniques. Here I am giving a formula like whatever input feature I am taking X, to that should be divided by NP is nothing but numpy, some numerical, so I'm going to use dot Amax. Amax is nothing but in that particular column. So I have a column like 213. In the first one 213. So in that take the maximum value, and in each column take the maximum value and divide that, divide each and every number of that column with that number. So this will process like 2 by 3, 1 by 3, 3 by 3. So that values will be consistent then. So that is the meaning of this. And Y label also I am doing normalization just by taking some constant number. Here almost all are similar. So I have considered a constant number. I'm dividing with 100. All my features now I'm going to divide with 100. So if this one and this one, now I'll get a nearby values of float. So if I divide this 92 by 100 bits, the value will be 0.92. So everything will be zeros, some point values. So now X and Y I can make it as a consistent values. Otherwise you can see here these are 2915 very low range and these are 9286 very high range. That will be no, we cannot plot that two values on a graph. For that I am doing the normalization. Next thing is, so when we are building artificial neural networks, so artificial neural networks I have already told you. So this is the input layer, and then this is the output layer, and this is the this is the hidden layer, and this is the input layer, and this is the output layer. So let's say here I have two nodes. I have two nodes. So now let's say this is my x1 and x2. So I already told you when it is going to hidden layer, we will add some weights to that inputs. We will add some weights to this input. So it may be some W1, W2, W3. and some bias we will add here. So the whatever input value it is coming, the value we are taking from that hidden layer will be now. So let's say H1. This node, let's say H1 is equal to the product of X1 and W1 plus this bias. So this is the value it will come from the hidden layer to output layer. So why we are adding weights already explained you yesterday. So weights means each node when you are performing something, each node will have a different value. Maybe to do some output, to get some output, maybe some nodes are most important and maybe some nodes are very less important. So every node, maybe these two nodes I cannot give 50% and 50% weightage. I need not to give, maybe this feature is maybe useless for me. So I can give the weightage for this node is 20 and this weightage is 80%. So depending on that, the weights will be updated. When if I give 80% and 20% weightage here, and when you process, if it is not predicted correctly, if the dog features I am giving, just assume I am dog features I am giving, maybe 80% weightage I am giving to eyes and 20% weightage I am giving to nose. When it is predicted in the output, it is, if it is predicted dog, it is okay. But if it is not predicted dog, it is predicting like cat, then what I have to do? I have to come back and now I have to update these weights. So means now I'll change this weightage as 80%, this node weightage as 80% and this node weightage as 20%. So I'll update the weights. That is what happens in back propagation. And why I am using bias means, for example, if I don't have a bias here, so for example, if you are making a dish, you are making a robot and the robot is now making a dish. Without bias means it's completely perfect. So if 90% of salty should be there, some 10% of sweetness should be there, then only the robot will perform any action. So without bias means if complete 100% accuracy is there, then only the performance will be, the action will be taken care. But if we are adding bias means if something is missing in that ingredients, if some salt is missing, but bias is like a mystery ingredient. So if something is missing also, the bias add up on that and it will give, it will make sure that the action will not stop. Just like if in that real data, maybe some feature is missing here. We whatever feature we want for our action, maybe that is missing. So by adding bias, the action will not stop. Something we are adding from external source, some input we are adding external source, so the action will not be stopped. It will perform well. There won't be any effect that some feature is missing. Some normally in real time data we won't get the clean data and we won't get the necessary features we want. That cases all we will add some bias here. So each and every node we will add one bias. The constant value will be there for bias. So this bias will be added to each and every node of our layer. So this is what happens to this particular thing. So while doing here, we are giving activation function in between this. So this activation function will tell which node should be activated and what weightage should be given to each and every node. So that activation function in our algorithm, here I am using sigmoid. So after input layer, here after input layer, I am using this sigmoid as my activation function. So sigmoid activation function already told you that this formula 1 by 1 plus y e power y equal to mx plus c. So that we are going to take here the same formula we are going to apply and we are defining that sigmoid function. And now time is only 5 minutes left. So just I'll go first with that algorithm, then if anything is needed tomorrow I'll explain. So here the activation function I have defined, sigmoid activation function formula I have defined, and I am asking the machine to learn about perform that sigmoid activation function, and then it is going to we are going to use gradient descent algorithm to minimize that loss. Whatever we are getting from sigmoid function, we are going to minimize that. Okay, now this is a bigger problem project, so tomorrow we'll continue the same experiment at the starting. Now I'll stop that this experiment here. Anyway, this link will be shared to you. Just go through it. You'll understand, and tomorrow we'll continue this talk. Now we will share you the feedback link, and of course this Google Colab link also we have shared it to you. Please go through that feedback link, and if any doubts are there for today's class, you please keep it in chat box. Tomorrow I'll read and I'll rectify that doubts. And we'll stop the class for today, and tomorrow we'll meet. Thank you.